So what can we do so far? We got several things we can do. We can calculate empirical formulas, we can calculate molecular formulas, and we can balance chemical equations. And so this next part is kind of a thing that people tend not to like, but also when you get it, it's a thing that people tend to like because it's always the same. The calculation we're going to do today is always the same calculation. It always works the same. It always tells you the same thing. And once you get it, that's should be free points for the rest of the semester. Because if you can do that kind of calculation, it's going to come up again and again. It's probably the most important calculation in chemistry. It's something that we do all the time, that when I'm working in my research lab, when any chemists are working in a research lab anywhere, they have to do these kinds of chemical equation calculations. So who's done these kind of calculations before? These grams to moles and that kind of stuff? Does anybody know a little bit about that? Okay, so you got a little bit of a start on that. That's great. We're going to talk about it briefly because we're going to need to do it on Monday in lab. This is not going to be on the quiz on Tuesday because we've got enough stuff for the quiz from the chapter 3 stuff. So this will be our next quiz, whatever that happens after Tuesday, but not on Tuesday. This will be a big part of the first exam for sure. Okay, so first of all, I don't really like this word stoichiometric. It's a kind of a big word. It's not really meaningful to a lot of people. All it is measuring amounts of and calculating amounts of reactants and products. So looking at a chemical reaction and saying, how much of each thing do we make? That's all that word means. I don't know why it has to have its own special word, but a lot of fields like to have their own special words. So these are the kind of problems that we're going to look at. If propane reacts with oxygen, we get water and carbon dioxide. What is the mass of oxygen that will react with 96.1 grams of propane? So you've seen a problem like that before? Some of you probably, maybe others not. The idea of this is that when we look at a chemical reaction, which we're going to look at. So let's first write the chemical reaction for this, and then talk about why we need to do this kind of a calculation in the first place. So propane is C3H8. We're going to react that with oxygen to get carbon dioxide and water. By the way, if you've got these notes from Blackboard, we're skipping the second half of the previous packet of notes that the other stuff was in because the book changed order, and so I'll go along with the book. And we're going to do these calculations first and then go back and look at types of reactions. So eventually you'll be able to write the products of different reactions just by knowing the reactants, but for now, we'll just look at the whole reaction so we can do these calculations. So here's a combustion reaction, like we just talked about. Is this balanced? It's not. So the first step is we're going to need a balanced chemical reaction. So let's look at our balanced chemical reaction. Can you balance that? See if you can do that, and then let me know what numbers you come up with. We got some numbers? What do you got?
So 5 in front of the O2, 3 in front of the CO2, 4 in front of the water.
Okay. So now we have a balanced equation, and let's think a little bit about what that really means. That means that one molecule of propane, so you got 3 carbons with 8 hydrogens attached, needs 5 molecules of oxygen. Those all react together in a 1:5 ratio. And then you make 3 carbon dioxide molecules and 4 water molecules. We did that diagram on Tuesday where I kind of drew out the pictures of the molecules so we could see the count of them. And that we could do that here too. But the important thing is that they have to react based on a count, not based on a mass. I didn't say a gram of propane reacts with some oxygen. I said a molecule of propane reacts with oxygen. And that's the reason we have to do this type of a calculation. Because we can't, the equation doesn't tell us anything about how the masses react with each other. It tells us about how the numbers react with each other. One of these reacts with 5 of these. But molecules are so small that we can't count them, right? We don't have our tiny molecule tweezers, so we need to weigh them. So that same idea when we talked about like the big jelly bean jar or something like that, where you can weigh things and then you can count them by weighing them when there's too many of them to count, applies to molecules. We want to count the molecules, but we have to do it by weighing them. And that's why we have to constantly be doing this kind of conversion. So we've got 96 grams of propane, and we want to know how many oxygens will react with that. So 96 grams is not a count, right? That's a measurement. So we need to get to moles instead. So there's this is kind of all written here, but let's just do it together so we could follow it. All right, 96.1 grams of propane. I'm sorry if you've done this before and this is boring, but that's okay. You don't have to pay attention. You got phones and stuff, right? You can just text for a little while if you know what I'm doing here. So we got that many moles of propane. We've got to figure out how many, or that many grams. We've got to figure out how many moles so that we have an actual count of propane. So how are we going to do that? How do we get moles? Molar mass, right? Yeah, like we've just been doing. So let's do that. How many grams of C3H8 are in 1 mole? I know. About 44. All right. So then we do that division, and it says right in there, we get 2.18 moles of C3H8. Okay. So now instead of a mass, we have a count. And we can say, for every this many moles of propane, we're going to need this many moles of oxygen. So if we had 1 mole of propane, how many moles of oxygen would we need? If we just had 1 mole of propane, we'd need 5 moles of oxygen. We get that from the balanced equation because we see right here that it's in a 1:5 ratio. So for every 1 propane, we need 5 oxygens. Okay, so then if we have 2.18 moles of propane, how many oxygens do we need? How do we figure that out? Yeah, you'd multiply it by 5. You see where that comes from? We're always going to need 5 times the number of oxygen molecules as we have propane molecules. That's what the equation tells us. Another way to do this, when these numbers get a little trickier, it's not going to be as easy as just saying, well, we multiply by 5. So we can also think of this as a conversion. This equation up here tells us that for every 1 mole of C3H8, we need 5 moles of oxygen. So we can use that as kind of a conversion type factor and really set this up like a factor, like another piece of a factor label type problem. So we can say 2.18 moles of propane, and then we could multiply it by a conversion factor that takes us from moles of propane to moles of oxygen. Now our equation tells us what numbers to put in there, and it tells us that we need 5 of these for every 1 of these. So in this example, the effect is the same. We're multiplying by 5. And that's going to give us 10.9 moles of oxygen. Now the question asks, what is the mass of oxygen that will react with 96.1 grams of propane? So we found the moles of oxygen. How are we going to get to the mass of oxygen? We're going to convert using molar mass. So we're going to take 10.9 moles of oxygen. We're going to find that there are 32 grams of oxygen in 1 mole. And that's going to give us 349 grams of oxygen as our final mass. So we need 349 grams of oxygen exactly to react with those 96.1 grams of propane. So that was kind of the individual steps. We balance the equation, then we convert grams to moles, we go moles to moles based on the equation, and then we go moles back to grams. Some people like to think of this as kind of an all-together thing. So let's put it all together. If this is confusing to you, just ignore this part, but some people find it easier. Another way to do this calculation is to think about it all at once as a kind of a conversion question. So we would go 96.1 grams of C3H8 times that conversion factor. Then times the, that's going to give us moles. I'm going to be specific with all my units here so we can see them. And then convert those that oxygen back to grams. Okay, so if you like to think of it all together like that, because it always is going to look the same, that's fine. So you'll always start with your mass of one reagent, convert it through the molar mass of that reagent, then the molar ratio of whatever two things you're trying to look at, and then finally the convert back to grams. All right, so however you like to do that, either in the 3 steps or as kind of all together as a conversion, that's fine. You can get a lot of information from this type of relatively simple calculation. So in this particular example, we said that for every 96.1 grams of propane, we need 349 grams of oxygen. But with the exact same technique, we can also figure out how much of each product we're going to make. So instead of comparing to oxygen, we could have done the whole thing with CO2 and with this 3 instead of the 5, and we would have figured out how much CO2 we form in this reaction. So we'll look at both of those examples. Okay, let's look down for a practice one here. Baking soda is often used as an antacid. It neutralizes excess hydrochloric acid secreted by the stomach. Milk of magnesia, which is an aqueous suspension of magnesium hydroxide, is also used as an antacid. What is the more effective antacid per gram, sodium bicarbonate or magnesium hydroxide? We're actually going to do this experiment in lab in a couple weeks. We're going to look at some different antacids and analyze which one's more effective based on this. But let's look at how we would use some of these calculations to figure this out. Because notice it says, which is the more effective antacid per gram? So that tells us that we're going to have to do some grams to moles conversions here. So I'm going to give you the equations to this, and then I'll ask you to do some of these calculations. So let's look at the two possible equations. An antacid is neutralizing excess hydrochloric acid secreted by the stomach. So we're going to take the antacid, sodium bicarbonate, and that's going to be an aqueous solution. That's going to react with hydrochloric acid in the stomach, which is HCl. And the products to this reaction are sodium chloride, NaCl, aqueous, water, liquid. Sorry, this is aqueous too. And carbon dioxide. Yes. So that's how it neutralizes the acid. You no longer, in the product side, we don't have any acids anymore. We just have neutral compounds, basically. So actually, it's going to make carbonic acid first, but then carbonic acid breaks down into these other products. So that's where we get those other products. Okay, the other reaction here is the magnesium hydroxide. Which reacts with HCl, and in this case, doesn't break down into a gas, but forms MgCl2 plus water. All right. So are those equations balanced? That's always got to be your first question when you have to do these types of problems. If you have to write down a chemical equation, make sure that equation is balanced. Are these balanced? No, it's not balanced. The second one is not balanced. So how would we balance it? Go ahead and do that. Let me know what numbers you come up with. Got some balancing numbers yet?
2 in front of the HCl.
2 here.
And 2 in front of the H2.
And 2 in front of the HCl.
Oh, wait. Sorry. Never mind.
I think that's right. Yeah. Okay, so we can say per mole that the magnesium hydroxide is the more effective antacid because it neutralizes 2 moles of HCl, whereas the sodium bicarbonate only neutralizes 1 mole. But that doesn't take into account the fact that they might weigh different. And the question asks us to figure out how much per gram is neutralized. So reword that question. This is saying, which is the more effective antacid per gram between these two? Can you reword that into a question that sounds more like this one? Sorry, that sounds more like this one. What is the mass of O2 that will react with 96.1 grams of propane? Because this is more straightforward of what we're supposed to do. How might we reword this problem so that it's kind of in that same format? How are we going to turn this into a calculation that's just like what we did? Yeah. Well, we're going to have to get to everything per gram. What then are we trying to figure out? Like, what is the goal that we're trying to get based on what we're told here? Yeah, we got to get a mass. Right. So how you want to give it a shot too?
Which chemical uses less mass to neutralize a certain amount of hydrochloric acid?
Okay, that's getting closer, but we still kind of have these vague terms like a certain amount. we need some numbers so we can actually start doing some calculations. So what might be a way that you turn this into some numbers? And it's somewhat arbitrary. You're gonna have to pick some numbers, but somebody give it a shot. How might you say this in a way that makes it like the problem we just did? Maybe let me ask that a different way. Does anybody have a good sense of how to do this problem from here? If I just said go find the answer, what would you do? Which one would neutralize more grams of hydrochloric acid? Yeah. So another way of saying that is 1 gram of sodium bicarbonate reacts with how many grams of HCl, right? Or how many grams, if we really want to make it exactly like it was up here, what is the mass of HCl that will react with 1 gram of sodium bicarbonate? And then, what is the mass of HCl that will react with 1 gram of magnesium hydroxide? And we didn't have to pick 1 gram. We could have picked 5 grams, 10 grams, whatever, as long as it's the same in both. 1 is a nice, easy number. So we could say, if we have 1 gram of this, and we have 1 gram of this, how many grams of HCl? How many grams of HCl can we neutralize? Can we react with? So how many grams of HCl reacts with 1 gram of each antacid? Now we're doing the same kind of problem that we just did, right? So let's do it. Do what we just did for each of these reactions and see if you can figure out how many grams of HCl reacts with 1 gram of each of these compounds, these antacids. See what you get. I'm going to set up one of these calculations here while you're working, and then we'll see. Did you get something like that for the first one? Okay, so we found that I found that here, and hopefully you found the same thing, that 1 gram of sodium bicarbonate neutralizes 0.428 grams of HCl. Okay, so we could do the exact same thing then with the magnesium hydroxide. The only numbers that change are the molecular mass. So instead of 84 grams, what did you get for the molecular weight of magnesium hydroxide? 58.3. And then our molar ratio is a little bit different because now we can have 2 moles of HCl for every 1 mole of antacid. And then we ultimately multiply by that same mass of HCl. And what does that one come out to? Like 1.2 something? 1.221? Okay, so how would you answer the question then? What's the more effective antacid per gram? Yeah, the magnesium hydroxide neutralizes almost 3 times as much HCl per gram. And we needed to calculate those masses to figure that out. One thing that we didn't talk about in this particular problem, but that we'll look at in lab, so does that mean that you should always use magnesium hydroxide as your antacid because it's better? Why not? Because there's other factors, right? For instance, cost. So one thing we'll look at when we do this lab is we'll look at the cost per gram of these different chemicals. Maybe one of them is a lot cheaper per gram, and so even though it's not as effective, maybe it's still more efficient to use that one from a cost standpoint. And then, of course, there's side effects and whatever else that you have to worry about with drugs. But this could be, we could say, at least at this level, that magnesium hydroxide is a more effective antacid per gram. Okay. So now let's talk about some pizzas. Let's say that here is our pizza recipe. Anybody getting hungry for lunch? Maybe. Are you gonna have pizza? Probably not. No. Okay. Well, maybe I'll change your mind after this. So here's our pizza recipe. For every pizza, you need a crust, 5 ounces of tomato sauce, 2 cups of cheese. Is that about right? Crust, 5 ounces of tomato sauce, 2 cups of cheese. So that means that if we had 4 crusts, we could make 4 pizzas. If we had 10 cups of cheese, we could make 5 pizzas. If we had 15 ounces of tomato sauce, we could make 3 pizzas. So let's say that's the total quantity of all these ingredients that we have. We've got a pile of 4 crusts, we've got 10 cups of cheese, and we've got 15 ounces of tomato sauce. What's the most number of pizzas that we can make? Just 3, right? Those extra crusts and cheese are just going to have to sit there because we don't have enough sauce for them. And we don't want a pizza with no sauce, right? Maybe you do. I don't know. I don't want a pizza with no sauce. Or we don't want to just dump extra cheese on stuff. So we have to stick to our ratios. That means we can only make 3 pizzas. So the same thing happens with molecules in a chemical reaction because they are counted in the same way that these things are counted. So when one of them is used up, it doesn't matter if there's more of the other ones. Those are not going to be able to react, and that's called we say that the one that gets run out first is called the limiting reactant. Have you heard of this before? Have you heard these sorts of things before? Okay, so let's look at what that looks like in a chemical type problem. Okay, we're going to talk about synthesis of ammonia. This is a really important reaction. Anybody know why this is so important? We take nitrogen from the air, react it with hydrogen, and make ammonia, which can then be made into fertilizer. So this is one of the major reasons that we can have agriculture and modern society is the invention of this reaction. It's a very, very difficult reaction from an energy standpoint. It takes a lot of energy to do this, a lot of energy. So if you can come up with a way to react nitrogen with hydrogen to make ammonia and not have it take a whole lot of energy, that would be like the biggest thing ever in the world. Seriously, it would be an enormous, enormous step forward. Unfortunately, probably not going to happen because of course, nitrogen is a super stable compound, N2, and so it's very difficult to break that up and make it into something else. But hey, somebody might find something, discover something, you never know. Okay, so the balanced equation for this reaction tells us that 1 molecule of nitrogen reacts with 3 molecules of hydrogen, and it makes 2 molecules of ammonia. If we've got 3 nitrogen molecules and 9 hydrogen molecules, will there be anything left over? So here we've got 1 and 3. If instead we had 9 of these if instead we had, whoa, hold on, what's going on? Again, if instead we had 3 of these and 9 of these, how many molecules of ammonia can we make? 6. So those are reacting in the same ratio. We need 3 times as many hydrogen molecules as nitrogen molecules. So if we had 3 of these, we had 9 of these, that's still nothing left over, and we make 6 of these. We call that a stoichiometric mixture of reactants. So that's where that word comes in again. A stoichiometric mixture means nothing left over. Because if we have 3N2 plus 9H2, we can make 6NH3, and that's still balanced. So you see that? All right, let's look at the next one then. If we have 5 molecules of nitrogen and 9 molecules of hydrogen, is that a stoichiometric mixture? It's not. Why not? Right, we can only take, if we only have 9 of these, those can only react with 3 nitrogens. And so those last 2 are going to be left over. So then we would call hydrogen the limiting reagent, and we could say that nitrogen is in excess. Those are the words that we use. The limiting reagent in this blue case would be hydrogen. And then this one is the excess. There's extra nitrogens there. Now note those numbers. It can be a little confusing sometimes because the 9 is bigger than 5. So sometimes people look at that and say, oh, well, the smaller number, that's the limiting one. But in this case, that's not the case, because you need more than 9 hydrogens to react with 5 nitrogens. How many hydrogens would you need to react with 5 nitrogens? 15, because you need 3 times as many. All right, so let's do another problem like what we just did with those other things, but now where there could potentially be an excess. So because we measure these things often in grams instead of in moles, let's look at it this way. If I said you had 25 kilograms of nitrogen and 5 kilograms of hydrogen, and they form ammonia, let's say which one is limiting, how much did we produce, how much ammonia did we produce, and how much of the excess reagent is remaining. So we can answer all those problems just knowing the balanced equation and those masses. So what do you think the first step is here? What would you do first to figure out which one is limiting? Is that louder? Yeah, we have to get to moles here. So kilograms to grams, grams to moles. Let's do that. So 25 kilograms is how many grams? 25,000 grams. And then nitrogen N2 is going to be 28 grams per mole. So that's going to give us 893 moles of nitrogen. And then got 5,000 grams of hydrogen. Divided by 2.02 grams is going to be 2,480 moles of hydrogen. Okay, so we've got our moles now. How are we going to find the limiting reagent? What would you do to figure out which one of those is limiting? Yeah, we'll go back up to the equation. Now in this equation, it's 1 to 3. So we could just multiply the smaller one, or multiply the nitrogen by 3 and see what the hydrogen is. But I want to do it a little bit more systematically, just so when we get to numbers that are a little more complicated, you can still do the same thing. So what I would do to figure this out is I would do it just like one of those other problems, where we look at the molar ratio and determine how much of one we need for the other, and then compare the numbers. So let me show you what that might look like. I might take the 893 moles of nitrogen and multiply it by that molar ratio. So I'm going to put moles of nitrogen on the bottom and moles of hydrogen on the top. Then I look at the equation and I find that those numbers should be 3 of these to 1 of those. That's the same thing as multiplying by 3, but in a lot of equations, you might not have nice numbers like that. It might be, 5 to 7 or something. So you'd want to set this up with those numbers like that so you can see it. All right, so we calculate that out. 893 times 3 divided by 1 is 2680. Which tells us that for every 893 moles of nitrogen, we need 2,680 moles of hydrogen. Now we can go back and look at our numbers. We've got 893 moles of nitrogen and 2,480 moles of hydrogen. So what does that tell us is the limiting reagent here? Hydrogen, right? You see that? We have less hydrogen than we need. If we're going to react all of those 893 moles of nitrogen, we need 2,680 moles of hydrogen, and we don't have that much. We have 2,480. So we can say, no, we do not have enough hydrogen and that one's going to be limiting. So that tells us now that when we do other calculations, we have to use that limiting one. So this next question is, what would be the mass of ammonia produced from this reaction? So we're going to take a number of moles of one of the reagents, compare it with the number of moles of ammonia produced, and do that calculation. But we have to use the limiting reactant here so that we don't overestimate how much we're going to make. Right? So let me show you what that looks like. We're going to take 2,480 moles of hydrogen, and then we want moles of ammonia. So we go back up to our equation, and we find that for every 3 hydrogens, we make 2 ammonias. So for every 3 hydrogens, we make 2 ammonias. Get that right? Just straight from the numbers from the balanced equation. And then we're going to find the mass of ammonia. So we're going to convert from moles of ammonia to grams of ammonia. Right, so that's 14 plus 3 is going to be 17 grams per mole. That's going to be 28.1 kilograms. So I did the conversion, but it's 28,106 grams is what I got on my calculator. What would we have gotten if we used 893 moles of nitrogen? Would we have gotten a bigger number or a smaller number? Would we have overestimated or underestimated? But we would have overestimated. Because remember, we have excess nitrogen. We have more nitrogen than we can react with the amount of hydrogen we have. So if we use that nitrogen number in this equation, we'd get the wrong product. We get the wrong product mass, and we'd overestimate it. We get too big of a product mass. So let's figure out how much of that excess is remaining. How would we figure that out? We have to figure out how much nitrogen this much hydrogen actually reacts with, and then whatever's left over, that's the excess. So notice here that all of these things that we're doing, it's that same calculation over and over again. Grams to moles, moles to moles, moles back to grams. We're always doing the same thing, just with different reagents in there depending on what's asking or what's being asked. So this time we're going to take that 2,480 moles of hydrogen, and we're going to react it and compare it to the nitrogen. So we're going to take moles of hydrogen and instead look at moles of nitrogen. Our equation tells us that there's 3 of these for every 1 of those. And then we can convert that back to grams. So that's 28 grams of nitrogen per mole. All right, so the amount of hydrogen that we have reacts with 23.1 kilograms of nitrogen. But we have 25 kilograms of nitrogen, right? So what's the excess? Yeah, it's the difference of those two. So the excess is going to be 1.9 kilograms. So we've got an extra 1.9 kilograms of nitrogen that we can't use in this reaction because we don't have enough hydrogen to react with it. Okay. All right, let's look at some more practice here because we're not going to go in some other stuff. We'll get into theoretical yield probably next time. Nitrogen gas can be prepared by passing gaseous ammonia over solid copper oxide at high temperatures. The other products of the reaction are solid copper and water vapor. If a sample containing 18.1 grams of ammonia is reacted with 90.4 grams of copper oxide, which is the limiting reaction, if any? And then how many grams of nitrogen will be formed? So this is kind of the full problem. This is as difficult as this can ever get. You're given some masses, you have to find the limiting reactant, you have to come up with an equation first, then you have to find the limiting reactant and figure out how much of whatever you're going to make. And this is not just an exercise here. If you ever have to do any chemistry in whatever you're doing in the future, either classes or work, this is exactly what you will do. These same types of problems, it comes up all the time. So see if you can work together on a problem like this. You got to come up with the equation, balanced equation, and then do just what we did. Convert those grams to moles, compare them, and see how they fit with the molar ratio, and try to find the limiting reactant, and then use that to figure out the theoretical yield of what you'll make. All right, let's give it a try. See how far you get before you get stuck, and then we'll look at it. At least try to get the balanced equation first, and then I'll stop you, and we'll do that together, and then we'll go on from there. All right, do you have an equation yet? Chemical equation? Do you remember ammonia? That one's given, huh? Actually, all the formulas are given, so we can do that. That's going to be gaseous ammonia, NH3, over copper oxide, CuO, makes copper, water vapor, and nitrogen. Is that what you got? Nitrogen gas prepared prepared, meaning made, by passing gaseous ammonia over solid copper oxide. So the ammonia reacts with the copper oxide, and we end up with copper, water vapor, and then that ammonia. Is that balanced? Anybody get it balanced? Not yet? You got it?
4 NH3 plus 6 copper, 2 oxygen, and then 2 nitrogen gas, 6 copper, and 6 water.
Okay. That would work. And that would, I think that's all balanced, right? But it is doubled. So it's not the lowest possible numbers. But for a problem like this, it should still work, right? Because the ratios are the same. We might simplify it. Make this 2 and 3. And if you can always kind of check that if you see that you have a bunch of even numbers. We can just simplify it like that. Divide everything by 3 or by 2. Okay. So now the question tells us that 18.1 grams of this reacts with 90.4 grams of this. Which is the limiting reagent? Anybody figure that out yet?
Copper 2 oxide.
How'd you find that?
I converted them both to moles.
Okay, so convert them both to moles. What do you get if you convert these to moles?
I got 0.06
Okay. Oh, 1.06? Oh, yeah, that makes more sense. Okay.
and then 1.14 moles of copper oxide.
Okay. So now we can see that these are approximately 1-to-1 in moles, right? 1.06 to 1.14. But the equation tells us that they need to be in the ratio of 2 to 3. So there should be 50% more copper oxide in moles than ammonia. And we don't see that. They're about the same. So that means that that copper oxide must be the limiting reagent. There's not enough of it. Another way that we can do that, we can see that, is by doing the calculation. So we can say 1.14 moles of copper oxide. And then the equation tells us that it's 3 moles of copper oxide for every 2 moles of ammonia. Oops, NH3. Right. So this tells us that for every 1.14 moles of copper oxide, which is what we have, we need 0.76 moles of ammonia. What we actually have is 1.06 moles of ammonia. So we have a little extra ammonia than what we actually need. You see how I found that? We have a little extra ammonia. So therefore, we should use this copper oxide amount to find the N2 formed, not the ammonia amount. That's why it's important to find the limiting reactant first, or the limiting reagent, because you need that to then go on and do the rest of the problem. And sometimes it's not as obvious. Sometimes it doesn't ask you which the limiting reagent is. It just says how many grams of nitrogen will be formed. If it does so, you still have to look for that limiting reagent. You can't assume that those numbers are matched up properly. You got to do that calculation first, so then you can go find the appropriate thing. So now that we know that this one is limiting, we can do the rest of this calculation. So we can say 1.14 moles of copper oxide times 3 moles of that for every 1 mole of nitrogen. That's how many moles of nitrogen will be formed. And then we can convert that to grams. Okay. So from those amounts, we should make 10.6 grams of nitrogen and have a little bit of ammonia left over. We're good? Okay. So another name for that 10.6 grams of nitrogen is theoretical yield. That's the answer to this question, how many grams of this will be formed? A better way to say that is how many grams should be formed, or what is the theoretical yield? Because in real life, chemistry is not perfect. Every single molecule of ammonia does not get converted into nitrogen. There are all kinds of reasons that you might lose some, and it's not an error. It's not error at all. That's just part of the reaction. Some reactions are more efficient than others. Some leave some stuff behind, and some do a little bit better job of that. So this number that we calculate is the theoretical yield, which you will never actually get. You won't actually recover that much nitrogen in this reaction because the reaction is not going to be perfect. So the other part of that is the actual yield. If you do a reaction, you're going to measure some amount of product that is actually produced, and it is not going to be the theoretical yield. It might be really close if it's a really efficient reaction, but it's never going to be completely perfect, the theoretical yield. So we're also going to look at the actual yield and the percent yield. So the percent yield, the percent yield is often reported in a reaction, and that's the theoretical, that is not right. The percent yield is the actual over the theoretical. So how much did you actually make as a fraction of how much you calculated that you should make in a perfect situation, and then times 100% because it's reported as a percentage. So as some practice with what we just did, and then this new concept, let's see if you can work this problem out. We've got methanol, which can be burned as a fuel. And we're making it by combining carbon monoxide and hydrogen. So we've got carbon monoxide plus hydrogen gives us methanol. You've got two amounts here, 68.5 kilograms of carbon monoxide and 8.6 kilograms of hydrogen. Combine those together and calculate the theoretical yield. Then it also tells you, if this is how much is actually produced, what is the percent yield? So how much of the theoretical yield did you actually get when you did the reaction? Notice here it doesn't say anything about a limiting reactant. So you're going to have to check that on your own. It doesn't necessarily say find the limiting reactant, but that's always assumed when you're doing these kinds of calculations. You got to figure out which one's limiting so you know which number to use in your final calculation. All right, see if you can work this whole thing out on your own or in your groups.
figure out how much another one would need to get a higher number, that means that what you started with is low, or the one you started with is not a lower number. Yeah. Right. Right, which is less than what. So that means that this was.
How far have you gotten so far? Mostly got it? Did you get an equation? I think I saw mostly a lot of equations. So what equation did you get? Anybody want to volunteer that with numbers? What's your balanced equation look like?
CO plus 2H2 yields CH3OH.
Okay, does that look like what you got? All right. What did you come up with was the limiting reactant? Limiting reagent. Anybody get that far yet? Hydrogen? So hydrogen is limiting? Yeah. You thought it was a CO? Well, let's look at the moles. What did you get for moles of each of these? So we've got, in grams, we've got 68.5 kilograms of this one and 8.6 kilograms of this one. What did you get in moles for those? Did we do those conversions? Mm-hmm. That's fine. What about for hydrogen? $300? Okay, that's reasonable. Is that what you got mostly? So that tells us that we need, like, we'll pick one at random. So let's pick CO and figure out how much hydrogen we would need. So for 2,446 moles of CO, we need 2 moles of hydrogen. All right, so that's double. So that's going to be 4892. So for the amount of CO we have, we need 4,892 moles of hydrogen. Is that how much we have? Do we have that much, or do we have less than that? We have less. So that tells us that our limiting reactant, assuming these numbers are correct, which, did anybody else get similar numbers? Yes? Okay. So that means that our limiting reactant must be the hydrogen, because we have less than what we need. So let's label that. This is how much CO we have. So then this is how much H2 we need. And then this is how much H2 we have, which is less than what we need. So that means that the H2 must be limiting. See where that comes from? Sometimes it's confusing. So please practice this and see where that comes from. Okay, so now that we know our limiting reactant is the H2, we can continue with the rest of the calculation using that. So we can say 4,300 moles of H2, and we have 2 moles of that for every 1 mole of methanol, and then we'll convert methanol to grams. Anybody calculate the molar mass of methanol? Do you have that number for me? What? About 32? Yeah, that's fine. We'll use that, right? Because it's 12 plus 16 is 28, plus 4 is about 32. Yep, that works. So that gives us $68,800 grams of methanol, or 6.88 times 10 to the 4th. Is that what you got? Yeah. So what is that number? Is that the theoretical yield or the actual yield? That's the theoretical yield. That's how much we could make if every single molecule of H2 was reacted and became CH3OH. Our actual yield is given up here, 3.57 times 10 to the 4th. So our percent yield is the actual over the theoretical and then times 100%. So we've got the actual yield, 3.57 times 10 to the 4th, divided by the theoretical yield, 6.88 times 10 to the 4th, converted to a percent. About a little less than half, or a little more than half, right? Yeah. So 51.9% is our percent yield. Is that what you got? We're close to that? Around that? Okay. So we use that mole calculation to figure out the theoretical yield and then compare the theoretical yield to the actual yield to get a percent yield. And that's what we'll be doing in lab. And we'll be doing these types of problems on Monday as part of lab. And there's a little bit of pre-lab practice for that too. So be ready. Also, as we said before, a quiz on Tuesday. So be ready for that. This stuff won't be on that quiz. The quiz will be on the stuff from before, the naming, the balancing reactions, and the empirical molecular formula calculations. So that's the stuff that'll be for Tuesday, but you can get started with this also. And then it's getting hot this weekend and next week, so please make sure to wear appropriate lab clothes or at least bring them. Got to have pants at least to the knee and closed-toed shoes so that we can do lab. All right, have a great weekend. Good job making it a quarter of the way through the class, and we'll continue.